we're thrilled to have Oliver.
Okay, thank you. Thank you very much. Well, it's great to be here, so thank you to the organizers. In particular, I was reading this morning on a sign on the college green that apparently the last time the British were in Connecticut, we extensively plundered New Haven, apparently. So, you know, I'm glad you let me back. So I have three things in my mind right now, which is firstly, it's been a long day. There's been some great talks, but I wouldn't, I understand if your brains are full. Secondly, I'm aware I'm the only thing standing between you and dinner. But equally, third thing, Andrew is here, and I'd like to sort of thank him for lots of things. So I'm going to do it, but hopefully I'm not going to do it in too scary a way. So that's the aim of what I'm going to talk about. So on a very personal level, day one of my PhD, I got given 3 papers to read. And I honestly can't remember what the other 2 papers were. From that moment, so, throughout my research career, this has been sort of somewhere there, somewhere driving it, somewhere guiding it. I wish I could write an abstract that compact, by the way. 1-sentence abstracts, how do you do? And yeah, we heard in the last talk, 1984, not quite April, March, so we should have had this meeting last month, but we're nearly exactly on 40 years of this paper. So, it's a good time to celebrate. And, maybe it's a little bit hipster to say, oh, well, I preferred Andrew's earlier work. I mean, but, this is where it all started. This is the beginning.
Well, there are precursors.
Okay. So I think to say thank you to Andrew really in 2 directions. I mean, firstly, in a sort of intellectual sense. So what he did was in this paper, he set a whole new direction on the central limit theorem. And the really key thing is he made us think about why the central limit theorem is true, that it wasn't just a kind of exercise in algebra and intimidation and writing down equations. There is a story that runs through this that I will try and share now about why the central limit theorem is true. And so I was very honored to work with him on this in the early noughties, as he mentioned. And I think that this is where the other sort of gratitude comes in. I mean, lots of other people have said this already, but I want to add my thanks to Andrew as a mentor. I remember we sat down in a cafe somewhere in that direction and sort of wrote the first draft of our paper together. And he sort of showed me how to do that, how to try and tell a story through writing a paper. The only thing that took me aback, I'll be honest, was it was about 10 in the morning and Andrew ordered a glass of cider. Now, if you're British, that has other connotations. So I was a little bit taken aback. Even for a British person, I was impressed, but now I understand. So what I'm going to do is I'm going to go back to his original paper, talk about our paper together, and then say something more recently that I did. Now, I don't need to show this slide because we've actually seen this in the last 3 talks. So this shows how fundamental this was. But just to remind you, we're going to say d of u, it's the KL divergence from u to a Gaussian with the same mean and variance. And here is the result. If d ever becomes finite, we take the standardized sum. If d ever becomes finite, it converges to 0. Now, that doesn't leave much. It's kind of cleared up the whole problem. And I think Max alluded to this yesterday as well. And it's kind of remarkable that the paper is only 7 pages long, that in a 7-page paper that you can do all that. Various things in there, lots of things if you delve into the paper and start unpacking it. So for example, the fact that this d, it can stay infinite forever. There's an example of a density such that d does stay infinite forever. And even more interesting perhaps, there's an example of a density or families of densities where it starts off infinite and drops down and becomes finite. So the sort of destiny of this, is exactly captured by this condition of becoming finite. There are links into previous talks. So there's a link with the EPI, subadditivity of this D, that it shows that working on the powers of 2 sequences is enough. But that's still hard. I mean, it's not obvious how you do that. And thinking about this, preparing this talk, I think the sort of slogan here is in red. Logs are hard. Logs are, anybody that's done anything in information theory knows that logarithms are annoying.
Unless you're taking logs of products.
Well, yes, okay. But you know, logs aren't generally nice things to play with. So the kind of first contribution of this paper really was to use this De Bruijn identity that I'll show you in a second that links this D quantity back to Fisher information. And the key thing is here, logs are hard, squares are nice. So the minute that you transform into Fisher information, then you're working in the world of squares. And squares are good because we have things like Pythagoras' theorem, that the whole of the Barron work you can understand in some sense as a story about Pythagoras' theorem, about projections. And so this is really the kind of key theme of what I'm going to talk about. But I would say even then, even when you have all these ideas, there's a lot of sort of delicate stuff going on. You know, you care with uniform integrability, the kind of stuff that, you know, you or I probably wouldn't do or wouldn't do right is there, and it's correct in there. Oh, sorry, so, right, so just to remind you about the Fisher information. So the Fisher information we're going to look at is just the Fisher information of a density with respect to the location parameters. So what we're going to do is we're going to take a density and we're going to define the score function to be, well, depending on how you think about it, either the derivative of the log or the ratio of the derivative to the density itself. And so sort of the nice idea with this is that what you can do is you can standardize the Fisher information. What you can do is you can define this quantity here, this j of y, which is sigma squared, that sort of makes it scale invariant, times then the difference between the score function of the random variable and then this rho of z, the score function of something else, the score function of the Gaussian. And so what this does is it kind of fixes the Gaussian into the conversation already. We sort of know where we're going. We want to get to the Gaussian, and the Gaussian is there. And the nice thing about this is that the Gaussian, this Gaussian score function that we compare with, is linear. So what we have is we have a perfect square involving the score function that we care about and something that's linear. So what we can see is that this whole story, the positivity of this J, which is a kind of hidden version of the Cramer-Rao lower bound, it becomes a story about score functions being linear. And that's nice. That's already the story. I said that we'd understand why the CLT is true. On some level, the CLT is true because the Gaussian has a linear score function. Now, particularly the reason that that's true, sorry, I'll come back to this. So the link is here. The link is this De Bruijn identity. So a little bit of the history of this. I think this is one of these results that's possibly not correctly named, though I'm not sure about it, in that it was first published by Stam. So it was published by Stam, but he called it the De Bruijn identity. So my guess is that De Bruijn proved it and didn't write it down, but Stam did.
Wasn't De Bruijn his advisor?
De Bruijn was his advisor, so I think it was something that they kind of talked about together. And this is a deep result. I mean, this links into, in some sense, this is a kind of hidden version of the heat equation. And you can go down a rabbit hole with this. You can start off with this De Bruijn identity, the heat equation. You can go into things like the Bakry-Emery gamma 2 calculus, lots and lots of sort of beautiful things lying not very far under the surface if you go in that direction. I'm not going to do that today, but there's some lovely things that this relates to. So the kind of summary of this is that De Bruijn is what he gave was a derivative form of this, and this is where this uniform integrability comes in, that Andrew proved this integral form. So this is what we have here, that d of x we can represent as an integral of these standardized Fisher informations. So specifically, of sort of perturbed Fisher information. So we take the x and we perturb it. We add a certain amount of normal into it. So taking the linear combination of x and the normal, that's the thing that we need to consider the Fisher information of, which is nice because this is probably a better behaved thing. And in particular, this was something that somebody else had already looked at. So there was this paper of Larry Brown's a couple of years before, so 1982, which considered something kind of close to this. So what Brown did was essentially he proved that in this sort of perturbed sense, this Sn perturbed by a certain amount of normal, he proved that it converges to something. So he has this kind of subadditive result that says, well, this thing has a limit. He didn't really get into what the limit is. He kind of conjectured what the limit might be. He kind of didn't mind because the reason he was doing this was he wanted to prove convergence and distribution. So he did prove the central limit theorem, but he proved it in a sort of classical sense. The result was convergence in total variation. So Andrew's contribution here is to show that not just does it converge to something, but that it converges to zero. But it's fair to say that the Brown work was very fundamental in this, that the Brown work was the sort of scaffolding on which Andrew's work was built to some extent.
To get the uniform integrability, I had to use some inequalities that were in Brown.
So, I mean, I mentioned this already, but this is, if the sort of one take-home result, this is maybe the take-home result, that the score function satisfies this lovely identity. I mean, identities are rare, and so we should grab onto them when we have them. And this is a really, really nice one. So if we have, I mean, you can state it in lots of different ways, but for IID, U, and V, if we define W, which is the sort of standardized sum of these, divide by root 2, do the sort of CLT scaling, then what it turns out is that the score of this sum is it's kind of the average of the scores, but it's a projection of this. So you take the sum of the scores of the individual variables, you take a conditional expectation. So this is a function of W given by taking the conditional expectation. So this is where the Pythagoras comes in. This is a projection. We're now sort of into the L2 kind of world. And this is an exercise. I mean, you can prove this. I mean, it's easier to prove the non-standardized version. But if you write out the convolution formula for densities, you differentiate it. If you're Andrew, you worry more than I would about the limits of this. But you can do this calculation. So what this means is that there's a kind of, you can think of it as a sort of Fisher drop identity. The fact that we have this L2 result means that we have this sort of Pythagoras theorem that says that, well, the difference between the average of the Fisher informations and the Fisher information of this sum, we can express as a perfect square. We can say it's the expectation of the square of the linear combination of the score functions and the score function of the sum. So what this gives us, or what this sort of motivates, is it motivates a kind of sandwich inequality. It motivates the idea that as the sample size gets bigger and bigger and bigger, this thing is wanting to converge to zero. There's a sort of subadditivity. This is wanting to converge to zero. So therefore, this thing, which is positive, is getting squashed. This thing is getting small. And so as a sort of, on a high level, what this does is it suggests that we should be looking at these kind of expressions. So G of U, G of V, so, take the densities, evaluate against the densities, and then this score. So this difference, difference between the sum of functions and the function of the sum. Now, it's hopefully clear on a sort of heuristic level that if you look at this, that if this thing is small, then, well, the sum of functions must be close to the function of the sum. And that feels linear. It's sort of a disguised sense of linearity. It's sort of saying, well, these functions, if they have this property, must be sort of linear. And as I say, that's good, because that's what we're aiming for. We're aiming for linear score, because linear score is how we're characterizing the Gaussian. So Brown's argument was to consider this kind of expression. And what he did was he slotted a different Gaussian distribution underneath it. He has this nice result that says if we have this perturbed density, what we can do is we can lower bound uniformly, we can lower bound the density of this U prime, this perturbed thing, by a constant multiple of a Gaussian. So what this means is that, well, if this thing is small, then it must be the case that this thing is small, that we can, we've got a perfect square, we can just replace the G terms by C squared times the product of the Gaussians. So instead of having to worry about this generally, having to worry about this expression in general, we can just consider the case where the weights, the densities on the outside are Gaussian. And that's nice because, well, it's nice for several reasons, but what Brown realized was that you could prove this using sort of classical ideas, using the Hermite polynomials, that the proof of the fact that this f is close to linear if this thing is small is proved by expanding f in the Hermite polynomials. The Hermite polynomials are orthogonal with respect to these weights, so you expand everything in sight in terms of Hermite polynomials. Now, sort of hidden in here, there is an idea that we'll come back to, that the Hermite polynomials are nice because they're orthogonal, but they're also nice because they're the eigenfunctions of this projection. So that's something we'll come back to, sort of towards the end of the talk. So it's sort of the clue is there if you know what you're looking for, coming back to us in retrospect. So this is where Andrew and I started working together. Like I say, the result is very deep, but it doesn't do everything. I mean, it does a lot, but for example, it doesn't say anything about rates. And this is sort of, I think, this is what Andrew suggested we might want to work on. And it took us a long time, took us a while. But we, from the beginning, at least Andrew knew what the answer would be. I mean, if you look at things like Pinsker, if you do sort of explicit calculations with things like gamma distributions, you believe that in general, this d of Sn should be behaving like O of 1 over n, that there should be a 1 over n is in some sense the right rate of convergence. And so we'd like to prove that. And so this is what we did. And so in our paper, what we do is we kind of, well, it comes together in stages, but the key idea is we go back to this sort of expression here. And what we do is instead of bounding this density below by the Gaussian, if you do that, you're leaving a lot of stuff on the table, so you can't afford to do that. So what we do instead is we do a sort of direct comparison. What we do is we bound this below by something similar. So we bound it below by something involving the derivative of f, that we find that the derivative of f is close to constant. And that's good. We're still in the same sort of linear world. The way that we do this is it's a sort of Stein's method type argument. What we do is we take an inner product between this thing and the score function. But now we've not got what we wanted, because what we've got is we've got the derivative of f, not f itself. So we have to pay the price somehow. So the price that we pay is that we can define, or there's a standard definition of something called the Poincaré constant. The Poincaré constant, people call spectral gap inequality, says that for a certain class of random variables, we can bound the derivative by a constant times the thing with the integrating back up, getting rid of the derivative. So if the Poincaré constant is finite, you can basically get rid of this derivative. You can go back up a step in the argument, back to the thing that you wanted. So roughly speaking, what this means is that if the Poincaré constant is finite, the Fisher information drops by a constant factor. When you double the sample size, the Fisher information drops by a constant factor. Now, I think this is an example of Andrew being a perfectionist. I was happy with this. I was like, yeah, that's fine, let's go with this. But if you think about it, it's not good enough. It's not the order 1 over n rate. It would be a polynomial rate, but it wouldn't be a 1 over n rate. So we did get there, but it took some very sort of clever ideas from Andrew that what you do is instead of thinking about doubling the sample size, you go to multiplying the sample size by n. And lots of sort of big, complicated pictures drawn on big pieces of paper to do with kind of Pythagoras' theorem in multiple dimensions and projections. But we got there. So what we did was we proved that, for example, if the terms have a density with finite Poincaré constant, then this relative entropy drops by a factor 1 over n. So that it's constant times something with an n on the bottom. So, we were happy with that. This is what we set out to do. Different people, Artstein, Bull, Barton, Knorr, proved the same result by very different methods. But, nonetheless, we were happy. We were happy that this 1 over n rate was what we were looking for. Except there's a kind of itch you want to scratch on this, which is that the Poincaré constant being finite is too restrictive. So requiring that the Poincaré constant is finite is not so good. It requires moments of all orders, for example. And we know that the CLT is true with with something like 4 moments, it should be true. Now, more recent work, there's a whole body of papers by Bobkov, Chistyakov, and Goetze that have kind of done this, that have got this sort of rate without assuming the finite Poincaré constant. And nothing at all against those works. They prove the result, but they don't prove it in the sort of Barron spirit. So what I'd like to do is I'd like to try and do something in the spirit of Barron, that, not by dealing directly with characteristic functions and all this kind of thing. So there's a sort of interesting perspective here. So we all know that it's not the case that if U and V have 0 correlation, that they're independent. We've all taught first year's probability, and they've all got that wrong, and we've all kind of beaten them about the head. But actually a sort of similar thing is true which is, and this goes back to this HGR maximal correlation. What you do is you define, instead of just looking at the correlation of U and V, you maximize over functions. You say, well, okay, you have a free choice of functions f and g. How big can the correlation between f of u and g of v be? And so it turns out that if this is 0, if this maximal correlation is 0, that does give you independence. Now, of course, the same is true for mutual information. We sort of know that this is true for mutual information, but mutual information is a pain. If you've tried to estimate it, for example, from data, then it's hard work. And there's, in a sort of learning spirit, we know that this covariance term we can estimate sort of nicely from data. So my belief is that this is a nice quantity. So how does it fit into the CLT story? Well, there's this nice result of Dembo, Kagan, and Shep that in the IID case, if we have Sn to be the sum of n variables, what they were able to do was they were able to say exactly what this rho max is, what this maximal correlation is. It's simply root m over n. And the way that they prove this, it starts, your spider senses start tingling when you see this. The way that they prove this is they prove it via these sort of successive orthogonal projections. They take this Efron-Stein expansion. You take a function, symmetric function, you can expand it as terms in one variable, terms in two variables, and so on. And sort of by doing all that and keeping track of all of the terms, that what they show is they show this result. Now, this wasn't my idea. Sort of bringing maximal correlation to the party actually came from Tom Courtauld. So Tom Courtauld in 2016 used directly this DKS result to prove monotonicity of J in the central limit theorem. So the obvious question is, okay, this seems a nice trick. This seems like a new idea. Can we use it? And yes, we can. Now, I'm looking at my watch and there's not a lot of time, but I just want to say something about how this works. So essentially what you do is you do a singular value decomposition. So, there are engineers in the room who will be happy to hear the word singular value decomposition. What you do is you can think about two operators here. So there's the kind of operator that we saw, that Cn is the operator where you take the expectation of f given the sum. Now, there is also an adjoint operator to this, so like the sort of transpose operator if it was a matrix. The adjoint is that you take the expected value of the sum given the value of y. So you have these two operators, C and C star, that are adjoints of each other. And what you can do is you can basically, well, you can think about C star C, and you can think about the basis of eigenfunctions, and you can do a singular value decomposition, essentially. Now, the reason that this is interesting is I mentioned before that in the Gaussian case, the Hermite polynomials were the things that were nice. These were the eigenfunctions. And so this feels like it's sort of going back. It's going past our, Poincaré stuff and going back into the world where, if everything here was Gaussian, we know exactly what the answer would be. And so we can say a little bit about these eigenfunctions. So for example, well, what we can do is we can take the eigenvalues and we can sort them. Now, there's a sort of trivial answer, which is you can get 1. F is 1, G is 1, the eigenvalue is 1. That's not very interesting. We'll park that. Next one down, the sort of most interesting, so the leading non-trivial eigenvalues are the things that give you the maximal correlation. It turns out that these eigenfunctions, the eigenfunctions that are the next level down in the SVD, are the things that give you the maximal correlation. And in the IID case, these are precisely the linear functions. So the linear functions are exactly the thing that's in the Dembo-Kagan-Shep result. That these are the sort of next best thing. The linear functions are the kind of next eigenvalue. The next eigenvalue down in this case is 1 over n. So what I thought is, okay, let's go one more stage down further than that. So let's look at what I call capital theta n. So capital theta n it's basically 1 over n divided by the next eigenvalue down, and then subtract off 1. So this is a sort of fancy way. I'm just sort of renormalizing the, 0, 1, 2, third or second eigenvalue, depending on how you think about it. Now, DKS tells us that this is positive. We've put these things in order, so we know it's positive. Now, the annoying thing is it could be 0. It could be 0, and I don't know how to deal with that. But what we can do is we can work entirely in terms of this quantity. And so this is what my paper August 2020, I don't think anybody was reading papers. We were all sort of hoarding toilet roll and swabbing our noses and things like that. So, you know, I wrote this paper, and I think this is the first time I've actually talked about this paper anywhere. But what you can do is you can do similar arguments that are based on these sort of projection ideas. And it's a two-stage argument. So the first thing is that what you do is you simply expand the score functions of y and the score function of s as eigenfunctions in the right basis, so in the sort of left basis and the right basis. And what that gives you is that the Fisher information of the standardized sum is divided by 1 plus theta of n. So there's an explicit bound on this 1 plus, on this Fisher information of the standardized sum. And then the other thing that you can do is you can do DKS again. You can do a sort of DKS type argument. You can go one more stage down the Efron-Stein expansion, and you can see that this theta of n turns out to be at least n minus 1 times theta of 2. So what this comes out with, if you put these two things together, is you get a 1 over n rate. You get that this standardized sum is the original Fisher information divided by stuff which has an n on the bottom. So I haven't assumed a Poincare constant. I haven't assumed a finite Poincare constant, and I've still got a 1 over n rate, nearly. So the kind of fly in the ointment here is that this is true if theta 2 is strictly positive. Now, I don't know if there's anybody in the room who's an expert on operator theory, but if there's anybody in the room who's an expert in operator theory who can tell me how I decide whether this is true or not, because my feeling is it should be true, right? I mean, it feels like most of the time it would be weird to have a repeated root, but I don't know how to rule that out. So anybody's got any ideas, I'd be very welcome to hear them. But if this thing is strictly positive, we've got a 1 over n rate of convergence. So, discussion. Actually, maybe we haven't done so much here. That what we've done is we've basically replaced one spectral condition from another. We started off with the Poincare constant. We've replaced it by this theta 2. Technically, we have weakened it. If the Poincare constant is finite, then this theta 2 is finite. So we've grown the set of things for which we get a 1 over n rate. But I don't know if we've grown it significantly. I don't know how much it's grown. But it still suggests that it's worth exploring further. And really, if nothing else, 40 years on, this technical report is still giving us ideas, still causing trouble. So I've had the 1-minute sign, so I'm just going to finish with an advert. So information theory and learning, we have an advert out. We have a hub in the UK, partnership between Bristol, Cambridge, and Durham. So you can work with me, you can work with Yanis on problems in this area. So if anybody's interested, the advert is there. The closing date is the 12th of May. So thank you very much for listening.
Yanis.
Thanks, that was great. In your last theorem, you only have the result for Fisher information. Can't you integrate?
Sorry?
You have that result just for Fisher information. Can't you integrate with...
It's a natural question, and I'm not sure. I think you should be able to, but I don't remember off the top of my head whether it's in the paper or not. I mean, the issue is what you need is you need control of this quantity sort of uniformly in. So, you know, if you had a summand x, you'd want control of this uniformly in perturbed values of x. And I suspect it should be true, but like I say, I don't know very much about this theta 2. I don't know how to prove it.
Suggestion, log-Sobolev.
Because it's for the actual values, it's not for the perturbed. So you can just do log-Sobolev and you immediately get the bound for it.
Okay, yeah, nice. Okay, nice argument. Thank you.
Yes, then you would need to assume, would it work though in terms of the finite, you'd be integrating the numerator j, so I guess, no, you just.
But you'd need to assume the density had Fisher information. It wouldn't just be true. It would need more smoothness.
It's not quite as general because log-Sobolev says that the relative entropy is less than the Fisher distance for log concave, but then your upper bound remains Fisher.
Not log concave.
Oh, I see. You're going to just use.
For the Gaussian, right? Because this is relative.
Oh,
satisfies log-Sobolev.
right. Yeah, yeah. Which, by the way, was first proved by Stan. Yeah.
And
Okay.
Andrew showed me that in a different coffee shop. I remember that. Yeah.
But integrating these things can be difficult. When we first got the 1 over n bound, assuming the Poincare constant, the form we had, we could not integrate over t. We had to change the draft of our paper so that it now said Fisher information in the central limit theorem, because we didn't, but we pushed and pushed, and we knew our competition had just gotten the entropic version, and the referee, the editors were saying, if you can improve this, we'll publish it side by side. And I remember slaving, that we were communicating back and forth, and luckily getting the picture right, we were able to get the form of the 1 over n bound to be one that we can integrate over t, the perturbation parameter, so that it could be an entropy inequality.
The difference is that here, this is not the third thing, this is for the actual algorithm, so you don't.
Yes. Oh, I see. There's no perturbation here at all.
There's,
I see.
yeah, there's no perturbation, but sort of implicitly, you're assuming that the Fisher information exists. You know, the relative entropy exists. Even if
You'd have to assume the finite J. So in the entropy limit theorems, you don't have to assume finite J's. They come for free with the convolution with the normals, if you can integrate the resulting bounds. Yeah. Okay, this has been fun. Was there, Chewy?
How does this assumption compare with the existence of the Stein kernel?
It's a very good question, and I don't know the answer. But I'm here tomorrow. I'm here tonight. We can talk about it. So yeah, I mean there must be some relation. I mean there's a whole sort of circle of ideas. I mentioned Stein methods already and Stein kernels and things, but I don't know if there's a specific connection and which way it would go. But
Okay, good. So let's thank Ali again.